Hello, everyone, and welcome to today's webinar on vehicle energy management and range testing for electric vehicles. Your microphones will stay muted throughout the session. If you have questions, we will address them at the completion of the presentation using the Q&A feature of WebEx. However, you are welcome to type in questions at any time. Please send the questions to both the host and the presenter so we can respond. We are recording this session and the presentation will be shared. Our presenter today is Mitch Marks. Mitch has an MS in electrical engineering from the University of Wisconsin-Madison. He has been at HPN since 2017, where he is the application specialist for electric motor testing. He first worked as a researcher at the university, working with traction motor testing and power grid research. Mitch, it's all yours.
All right, now looks like I've been unmuted and we should be good to go. So thank you guys for joining today. The topic today is drive cycles, electric vehicle certification, and vehicle energy management. This is really going to discuss about taking a vehicle at a system level and understanding how it uses energy, and then hopefully understanding it so we can improve that energy. I did a lunch and learn a couple weeks ago on the topic of drive cycles. We're going to touch a little on those today, but this will hopefully be a nice continuation for anybody who attended both. And test out my pen and let's get to it. So today we're going to cover a couple topics. First and foremost is why we care about range. I think everybody here probably knows that, but it's always good to start at a nice grounded basis. We're going to go through some test procedures for range certification. Really, how are we testing these, and how are we figuring out how far a vehicle can go, how efficient it is. We're looking at some challenges in dynamic power measurement. We're going to look at why dynamic power is different, why it's challenging to measure. And then we'll touch on some testing solutions. No free lunch, so you get to see how we help you achieve these goals at the end. So why do we care about range? It really comes down to when we buy a vehicle, we go up to the car and there's a sticker on the window that says, here's your fuel efficiency. You have this 119 miles per gallon electrical equivalent. And this is telling us how efficiently the vehicle uses energy. Basically, for the equivalent amount of energy in a gallon of gasoline, how far can this car go? And it's also telling us the range, the kind of, with this battery capacity at this efficiency, we can go this far. So these are two really important numbers because it, one, lets us know how far we can go. Kind of gives us this basis for, does this vehicle fit my needs as the consumer? It allows us to compare vehicles. We can see here that this test is run by the EPA here in the US. So it is a certified value, and it is something that we can use to compare one car to another. So it's not just we're taking the word of somebody. There is a governing body that gives us this number. So we can make decisions between vehicles and make educated decisions. We can understand how efficient a vehicle is, when it comes down to environmental safety and compliance with standards. This allows us to do that. And it really, I hate to say it, but at the end of the day, it comes down to marketing too. When a company wants to sell a car, we need to be able to market it. And right now, the longer the range, the more marketable that vehicle is. So it's going to allow marketing teams internally to come out and give us these really wowing numbers so that we can sell cars. So this is what we're going to talk about today. We're going to talk about getting to this efficiency and getting to this range. Okay, but first we need a little background, and this is going to be a little bit of a review for people who were in the lunch and learn session earlier, but drive cycles. So what is a drive cycle? A drive cycle is a series of speeds versus time that replicate real-world driving conditions. So in this US 06, we can see an acceleration, deceleration, hold, acceleration, deceleration, stop, acceleration, maybe a highway, and then some start-stop. So this is really what's a real-world scenario the vehicle might go through. And there's lots of these drive cycles. They're there for heavy test, or for heavy truck. They're there for city. They're there for highway. LA 92 is a highway pattern where we can see we're just holding speed and kind of maybe following somebody on the interstate. So it's really simple. It's a series of speeds versus time under simulated road conditions. We're going to be looking for city and highway mileage. There's going to be a torque profile that's simulating road conditions and vehicle drag. So we're really looking at how will this vehicle perform in a controlled scenario? How can we run these drive cycles and compare one vehicle to another as real as possible? And there's going to be a driver that's actuating the pedal to match these speeds. Okay, so now we know what a drive cycle is. It's just a series of speeds versus time to replicate real world scenarios. Now we can kind of dig into the meat of what we're here to talk about. And when we're running these drive cycle tests, it's pretty straightforward. We're going to be measuring battery current, battery voltage. Oh, there's teen current. And we can see that battery voltage, that battery current is kind of pulsing. This is an acceleration, a hold, start, stop, start, stop. We're going to be calculating the power. So this is the DC power used by that battery. But what we're really after is energy. How much energy did that vehicle consume during these various points? And we're going to look at that summation of the energy over time. And we can see we accelerate, we get a large change in energy. This is really what we're looking at to understand. So this is a little background for what we're going to discuss now. We're measuring voltage, current, power, energy. We want to understand how to make this number as small as possible. Cool. All right, let's talk about range testing. So I mentioned we're going to talk about a couple of different range types, or a couple of different range testing types. So I really see this as there's three types of range testing. There's the certified test. This is the one that the EPA or the governing body is going to do. This is the test to tell us, here's your range, this is what we approve, here's your efficiency, this is what we approve, and this is what's going to allow us to accurately compare one vehicle to another. This is going to give us those controlled conditions so that we do know we're comparing apples to apples. And this is that value that can be put on the window sticker. This is the thing we can market. This is what we can come out and advertise. This is what consumers can make educated decisions on. So that's our certified test. This is the one the government does. Now we just don't hand the keys over to the government. We want to understand what our range is before we test. And we want to make that range as long as possible with the components we've chosen. We're going to run the engineering range test. We're going to do this in-house, or we're going to do it at a test house that might have the facilities. And these are going to be a little more complicated. In the EPA test, or the certified test, all we care about is battery energy. But in the engineering test, we want to know how each component uses energy. We want to understand the effects of each subsystem. We want to look at those vehicle level control issues, and we want to understand vehicle level loss patterns. What does this mean? A vehicle just doesn't have one motor. It might have 4 wheel motors, 2 axle motors, heating, air conditioning, auxiliary, heated seats, all this stuff we enjoy, cooling pumps. And we want to understand how each of those interact so that we can make changes to the vehicle level control and maximize that range for a given component. Or if a component is really terrible, we might want to change that component or update a control or do these individual component tests to understand how they use energy. This is details. This is details at the vehicle level. Lastly, because we're making decisions on components, whether we want to change them, we want to update our control schemes, we want to find a new supplier, we're also going to do component level range tests. And these are a little different because they're a lot more detailed, but we're going to look to improve the losses of components. Maybe we change when we turn on a cooling pump. Maybe we change out a heating unit. Maybe we update the inverter control for our propulsion motors. But the point is to really understand at the component level how the losses happen and how we can make changes to update them. So these are the backgrounds. So let's look at some of the details. All right, the certified range test. Remember, this is the one the government does. All right, what do? Well, we need to characterize the vehicle rolling resistance. So we're going to take this vehicle out, we're going to spin it up to a certain speed, and we're going to put it in neutral and coast down. And we're going to see how the friction of the vehicle, how the air resistance of the vehicle affects it. This is really the rolling resistance. So we're going to characterize that. That's what's going to give us this real world ability to characterize this vehicle's range. We're going to instrument the vehicle DC bus. And if you've got one battery, we're going to measure one voltage and current, and therefore one energy. If you have two batteries, we have to measure both. But we're looking at how much energy the vehicle is using. We don't care about the components. We just want that vehicle level. How much energy do we use? How far did we go? This is how efficient we are. This is our range. So we're looking at that efficiency and range. But we're measuring that DC bus value. We're going to run the vehicle through a number of drive cycles from full to empty. And how are we going to do those drive cycles? Well, we went over what the drive cycles are. We're going to take our car, like the car we have here, and we're going to put it on a chassis dynamometer. And we can see that we have this little rolling road here. This is basically a treadmill for cars. So each tire has a little rolling road, and we're going to run the vehicle through these drive cycles from full to empty. And this little dyno, this is going to take into account that rolling resistance. This is going to take into account that vehicle dynamics. And we're going to characterize this vehicle's efficiency and range over these number of drive cycles. So we put a car on a chassis dynamometer or treadmill, and we run it through those drive cycles from full to empty. We record the range, we record the energy usage. And we're going to execute this test several times because we want a good average. So we're going to run it a handful of times. Different governing bodies use different number of runs. And also, depending on what part of the world you're in, you're also going to run a hot and a cold test. So there's environmental factors as well. But again, we're looking at that total energy used to get efficiency and then the range. And that's what we're doing. Then we get that sticker, and that tells us how far we can go. So that's a certified range test. One measure, or one voltage, one current, one energy. Now these things get a little more complicated when we get to the engineering level. Because if we look at my little animation on the side here, we have DC-DC converters, we have ancillary loads, which could be, heating, cooling, auxiliary systems, all these other things, these creature comforts we enjoy, cooling pumps, propulsion. We want to understand how each component uses energy. We want to understand the DC power of each component. And when we start looking at these new vehicles, excuse me, we're going to have multiple motors, front and rear axle, four-wheel motors. In heavy trucks, we're seeing all kinds of motors. Heating, cooling systems, infotainment. These are all going to have DC measurements. And it's not uncommon to see, 10 to 20 different power sinks that we need to instrument. So that's 10 to 20 DC powers. So this is a lot of measurements we're potentially looking at. Oh, man. We're going to run that exact same test we ran in the certification test, just with all these measurements. Okay, same test, car, chassis, dyno, energy measurements, a lot more energy measurements. Because we have these many measurements, we have many configurations. This can create some challenges because we not only need to get an instrumentation into the vehicle, but we need to have a sanity check, and we need to have all these systems coming into one location and some visualizations to know what's what. And sometimes we need to do some clever math to how does the front half of the vehicle operate? How does the rear half of the vehicle operate? We're going to record data throughout these tests and record the whole data file. And this is going to allow us to make decisions and control changes. We want to understand that while we accelerate, maybe we want to turn one system on and turn one system off to preserve efficiency. And we're going to want to have data to be able to make decisions on these different topics. If we want to change a component, if we want to update a control, we need to have data throughout this whole test for all of these components to make these educated decisions. And this is, once we've instrumented all these sources, once we're recording data on all these sources and running it through these drive cycles, we're really going to understand that vehicle energy flow so we can manage it and make decisions to change components, update components. So this is a really powerful test when it comes to taking a vehicle and making it as good as possible. Okay, so now we understand the engineering range test. We're doing the same test as the certification, just with a lot more measurements, a lot more data recording, and we're making engineering decisions based on this information. Lastly is the component level test. Once we've identified that a component might use a significant amount of energy, we're going to want to make component level changes. So what are we going to do? Now we're maybe not going to be on the chassis dynamometer, but we're going to be on a direct drive dynamometer that has precision instrumentation for torque, speed, voltage, current, electrical energy consumption. We're going to look at these details now. We're not just looking at DC, we're looking at AC as well. But on this direct drive dynamometer, we're going to run the same test profile. We're going to make detailed measurements on all channels, and this could be AC, torque, speed, temp. We're going to look at all these different measurements, and we're going to do a really detailed analysis. And we're going to figure out how to improve that component efficiency and how to improve that range. And we're going to take into account things like dynamic losses of components. We're going to look at, if we're looking at a motor, copper loss, iron loss, all of these different things, so we can start to make decisions on how to better operate these machines. But again, we're running that same speed profile versus time. We're just taking even more measurements and even more precise measurements. So at the end of the day, we're running the exact same test. We're just now doing it with more detail so we can understand these individual components and make those changes to improve our vehicle level range. It's a really powerful process if you think about it, going from certification level down to component level and running the same test at each point. All right, so I've mentioned dynamic power a couple times now, and I'm going to go into challenges of running these different tests, but I think we need to have a little bit of an understanding of why dynamic power is different. And I have a single graphic that I think illustrates this really well. So when we're running these drive cycles, our speed is constantly increasing, decreasing, starting, stopping. We get this profile. Why is this different than a steady state measurement? Well, when a motor is started, stopped, or changes state, there are losses associated with that state change. And rather than tell you through words, I think this picture on the right-hand side does a really good job of explaining it. So we have a machine, it's spinning at a certain speed, and then we apply a load to it. And what I have on the screen here is just a single phase of current, because a single phase of current illustrates my point. And we can see we have no torque, so we have no current, and then we apply a load. And we can see we get this really kind of big spike. We get these peaks on current. What is this? This is an inrush current. This is a loss associated with dynamics. And then we can see that current settles out to kind of a steady state operation point. Okay, why do I care about this? Well, if we look at our power, reactive power, apparent power, we can see when we get that inrush current, we get this spike in real power in black, and then our reactive and apparent power in pink and red. These are losses, because as that machine is settling out, we can see that go down to a nominal level. But we have this additional loss in that transition period. And if we're not measuring this signal correctly, we're going to miss all of this. We're going to miss all that additional loss. So when we go to do our component level test, or we go to understand the vehicle level test, we're missing these dynamics. That's no good. And these losses are constantly there in a drive cycle. And we need to characterize these dynamic losses so that we can get a decent measurement and really understand how to improve our components. So when I talk about dynamics, this is what I'm talking about. And in a moment, I'll talk about how HBK measures these quantities really well. We have this little black square wave. This is a thing we call cycle detect. This allows us to measure these dynamics really well. We'll speak on that more in a moment. Okay, Dynamics have additional losses. We're running these drive cycles. Drive cycles are constantly dynamic. So what are some challenges in drive cycles? And really these challenges related to dynamic power measurement. Well, for the certified range test, one of the challenges is having transparency to equations. We really want to know what the measurement period is and how energy is calculated so that we can not only get a number, but understand where the number came from and have confidence that it's correct. We want to be able to know exactly the period we're using, how the energy is calculated, when we're resetting the energy calculation, when the energy calculation starts, because it's cumulative. We really want to know how these are being executed. We don't want a black box. That's one challenge, is understanding the equations and not only how they're executed, but when they're executed, because energy is cumulative. If you have energy accumulating before the test starts, that could be a real problem. We're going to have limited access to measurement points. We make vehicles so that they don't fall apart and so that me and you can't just go and grab high voltage cables. So physically getting to some of the measurement points can be a challenge. And I won't belabor this, but getting sensors and getting measurement in can be really difficult if there's short runs or difficult places to place sensors. A lot of these tests require feedback to the dyno. Many times the certified instrument by the governing body is the dynamometer, and you want to have a real-time feedback from any instrumentation to the dynamometer so that it can be the certified instrument and you can monitor the test in real time. You want that feedback. We mentioned that these tests are running from full battery to empty. These vehicles have significantly increased ranges. These tests could take 10 or more hours. You don't want to have to rerun a 10-hour test. You want that feedback so you can know if something's going wrong immediately. You need to operate in a wide temperature range. You have to worry about electrical noise because we have these high frequency inverters. We really do have to be concerned with, is my cabling correct? Is my instrumentation isolated? All of these things to make sure we're not worrying about electrical noise. Because there's a lot of inverters, there's a lot of EMC, EMI. Lastly, accuracy. Accuracy is really important because if we have a vehicle that has a 500-mile measured range, but we have an uncertainty of 50 miles, we can only certify that vehicle for 450 miles. We can lower that uncertainty. We can raise that effective range. So accuracy is also important. So these are considerations for the certified test. Now, if we remember back, challenges in the engineering test are going to be the same as the range test, just more of them. Again, limited access to voltages and currents. We're only going to be able to get at certain measurement points. We might have to hack some things together, change some cables, but we're going to have limited access to those voltages and currents. Again, if we remember, we have 10 to 20 measurements with many configurations and many different ways to look at it. And what I have on the right-hand side here is a screenshot from our software, which tries to simplify this configuration, where we have 2 batteries, we have 2 inverters, we have 2 motors, and we have 4 wheels. And we try to break it out so you can understand the power usage of each component. And this is really inspired by these many measurements and many configurations. Because if you have 10 different power using sources, you can view the voltage, current, power of each individual component and have a unique name with it so you can understand what your system is doing, even for these complex configurations with many measurements. There's no steady state frequency. This comes back to that dynamic power. The speed and torque is constantly changing. We really want to understand, what is the measurement period for DC power? Again, if we're coming back to make decisions on changing components or updating controls, we want to make sure we understand where these measurements are coming from to make decisions. So we want to know the period for DC measurement. We also want to know how the integration's performed. Because again, if we're making these decisions, we want to have very correct information. We want to know exactly how it's being performed, and that also helps us correlate back to models if we're doing a vehicle level model. These vehicles are constantly changing states. We have transients, we have clutches, we have multiple machines phasing in and out. Again, right in line with this no steady state frequency, right in line with those drive cycles and understanding that dynamic power, we want to be able to pick up these transients, clutches, and multiple machines. We want to have that data recorded for each of these measurements for that entire test period, that 10+ hour test, so that we can understand each interaction. We can see the energy flow between these, even as things are phasing in and out. Because that dynamic power, catching those dynamic scenarios, is really important. And we might want that down to the millisecond or less range. We might want that really fast update rate. Again, this is something that HBK can help with. And then lastly, torque is difficult to measure. If we really want to kind of understand the components, we might have to take wheel torque and then get that back to some sort of calculated value. So torque is difficult to get to, mainly because placing a sensor in the vehicle is challenging. But from the electrical end, because we want to understand power flow, we want to be able to take many measurements in one location. We want to be able to visualize them. We want to know how power is calculated. And we want to be able to trust our dynamic power measurements. So there's definite challenges because there are a lot of measurements and it does execute for a long period of time. Component level drive cycle test. Because now we're measuring AC, this no steady state frequency becomes even more important. Vehicle speed's constantly changing and we want to trust that value in the dynamic periods. We want to look at these constantly changing states and understand them. We want to measure dynamic torque and speed. We want to know what our torque looks like in a transition if we clutch in a motor, because we don't want to overshoot and we don't want to get there too slow. It's a really challenging thing, dynamic torque and speed. And then a lot of times we'll want to relate these signals back to the CAN bus. And I haven't talked about CAN bus yet, but the vehicle is speaking to CAN. Each component is speaking to the vehicle controller over CAN. And the vehicle itself is estimating what its parameters are. It's estimating its power output, it's estimating its torque, and it's publishing this on a CAN bus. And at the component level, we want to make sure that what the vehicle is thinking matches reality. So we can measure the CAN, we can measure the real signals, and we can compare reality to vehicle. And we want to make sure these match. So there's additional challenges of dynamics, of constantly changing states, of dynamic torque and speed, and then of correlation to other values. So the component level test is difficult as well. And if we can correctly characterize the component and we can correctly characterize its CAN bus, we can then bring that back to the vehicle level test and improve that range. Cool. So we've looked at challenges in the 3 different types of testing, and a lot of it comes down to understanding our measurement period, having a high rate of data, and having many measurements in one place. So how can HBK help with drive cycle testing and dynamic power? Question I'm sure you're all wondering, and we do have a really powerful tool, so please stay tuned in. We have some key benefits, and here's our HBM power analyzer. One of them, we have a variety of sizes, and this is the beast I'm going to be talking about. We have transparent data and equations. We record every data point, and we give you all the equations so that you know exactly what data is being used to make a calculation and how the calculations are being executed. And if something goes wrong, you can rerun a test in data. Our test setups are flexible for many channels. We can measure more than 50 power channels into one common data file, so that even for your most complex vehicle setup, you can make a little graphical user interface, understand how each component uses energy, and have this really flexible setup where you can configure it to look how you want. Again, we record all the data, and we have a wide host of triggering. So if you just want to record power values, for the whole 10 hours, but every time pump 3 kicks in, you want to trigger and record that data. You can have high rate data on the triggers and low rate data for the whole test. We can do a lot of cool things with data so that you can really understand how your test is executing and make those difficult decisions when you're updating your vehicle controller or you're doing your vehicle energy management decisions on components. We can also bring in CAN into the same data file. So while you're measuring these real signals, these real powers and energies, we can measure the CAN bus to understand what the vehicle is thinking as well as reality. We have some great features for our dynamic power measurement. I'll speak up more on those in a minute. And we have the highest DC accuracy and very high accuracy for a wide variety of AC frequencies. So I'm going to elaborate on a couple of these points, and I think you'll learn something. So our testing is auditable. All the data is recorded. All the equations are public. And what we're doing is eDrive is storing all the signals to the hard disk, to the hard drive. And we have some new data modes for extended testing, where in the example on the right-hand side, I'm just recording RMS and power values. So I have my RMS voltage and current, and we can see those kind of changing state here over a small segment of a drive cycle. So we're speeding up, slowing down, speeding up, slowing down. We're doing some maths to figure out our speed. We're doing some maths to calculate our power, and we can see, during this acceleration, we have some power. Over here, we have some regeneration where we can really understand how the vehicle is regenerating. Regeneration is a big part of this. And then we're calculating that energy, see how the vehicle uses energy, how we put it back into the battery, how we drain it. And we're even catching transients. And this was a machine actually experiencing some airborne activity where the power levels fluctuate greatly. But this could be a transient, this could be a clutching in of another machine. We understand in great detail, because we're recording the data at a high rate, what's happening in the transient scenarios. We can allow you to set up custom equations. So if this energy calculation, we want this to involve 2 or 3 motors or a subtraction possibly, we can do calculations for that. You can understand how all calculations are done. And we have a wide variety of custom equations that allow you to adhere to standards today, because the standards today might be different than in the future. And because we give you the ability to edit the equations, not only see them, but edit them, you can update your equations to match what the standards are. If that means we're going to higher update rates, or that means we're going to different calculations that need to be used, you can be resilient to that. So really cool stuff. Again, we're flexible for many channels. So this is an example of we have a battery, 2 inverters, and 4 wheels. And we map this powertrain to have our battery, our DC power, our 2 inverters. We can look at the energy of each component, and then we can understand kind of the gear and system level losses by looking at the wheel torque. But we also have things like HVAC, infotainment, cooling pumps, heated seats, and we can add expansions for these as well and understand how each of these use energy as well. So we can really start looking at, again, how each component uses energy in the vehicle. The cool stuff, and this will help with the engineering range test. And I should mention, this is a feature in our software where you can set this up and look at this configuration and have a visualization. So this is taken from our software. Trying to make life easy for you. We have the highest DC accuracy and this cool thing called cycle detect. So cycle detect is how we measure dynamic power. It's what lets us be one of really the only people in the market who are doing this very well. We have our phase A current coming in red, and we're monitoring for 0 crossings. We take 2 successive 0 crossings, and we get this little square wave. This is our cycle time. We're doing our power, efficiency, reactive power, energy calculations on this half-cycle basis, which really makes us extremely accurate in the dynamics. This is a really powerful tool, because if you're ramping up speed, ramping down speed, you have confidence that your power measurements are correct and catch things like those reactive power overshoots or that extra power during transients. and we have this just really killer accuracy. So you can be confident that your measurement is as good as possible. What cycle detect allows us to do, and this is just an example of a dynamic test with cycle detect, where we had a vehicle that started moving, and we can see the currents start, and the currents are in red, and our cycle detect is just tracking that current as it's ramping up in both torque and speed. So we can have a lot of confidence tracking that. On the bottom, I have my power measurements, so I have my real reactive apparent power, and we can follow that power like a scope trace. And we can really start to understand the details of how that controller is executing that vehicle level control. We can see things like power overshoots, and we can start to understand how each component uses energy in either that certification level test, in that engineering test, or in that component level test. And we can really understand the dynamics of those real world scenarios. Super powerful tool for understanding how our power energy is being calculated and trust it in those dynamics. We offer feedback, so we do all those measurements in the unit. We can feedback those values to the dyno and act as a smart sensor. Because we're executing all our equations in real time, we can feed those back. We can also pull data from the CAN bus or correlate to the CAN so that we can have that system level understanding. But we can communicate with that automation system, have the user visualize everything in the lab, and be off to the races. So, conclusion, range testing is a really important part of vehicle certification and marketing. You know, we need to have that range to market, and we need to have the longest range possible to sell more vehicles. There's a lot of challenges measuring. We need to understand what the equations are. We need to understand the individual data points going into that. And we need to do it for a really long time. We need to measure this test for hours and have confidence that we're getting accurate measurements. Testing can be done on a component level, a chassis dyno, or in some instances in vehicle. And I didn't touch on this, but some of these drive cycles do have an in-vehicle component. And lastly, HBK, we have a really great knowledge set on this. We have some really great tools for understanding vehicle power flow and drive cycles. And we'd be happy to discuss anything further with you and how you can potentially bring these tests into your own lab. With that, I'd like to thank you. Please shoot any questions. And if you want to learn more about products, feel free to scan this with your phone and peruse what we have. So with that, thank you, everybody, and look forward to speaking with you.
All right. Thanks, Mitch. Everyone, I will be sharing Mitch's presentation with everyone who's here today. We also will notify you when the recording of this presentation is available for on-demand viewing. We do have time for some questions, so if you want to type those into the WebEx Q&A, please be sure you send them to both the host and the presenter, and we'll read a few here and get some responses live. All right, Mitch, how long and at what rate can you store data for the engineering range test?
Yeah, I guess I talked a lot about storing data, but I didn't really mention any specs. We can store the high rate data at up to 2 megasamples per second per channel. And we can store that for as long as you have hard drive space. But as I mentioned, these tests can take a really long time, in the range of tens of hours. So you might not want to store that high rate data the whole time. But what we can do is store the slow rate data, which would be like the calculated period. So let's say you're calculating power at a 1 millisecond level, so 1 kilohertz. We can store that for a very long period of time, and then have triggers to take that high rate data if you periodically need it. So we can store an absolute ton of data on a ton of channels. It just matters how much data you want. So as long as you have hard drive space, we can store data.
All right. Where do these tests get executed?
I think that would physically mean where the test is being executed. So these will largely be in climate-controlled chassis dynos. Some people have the luxury of having on-site chassis dynos for this purpose, but they are really expensive because it's a climate-controlled room. So there's plenty of partners out there who have certification or I shouldn't say certified. They have range testing sites. I think Millbrook in the UK has one. I know FEV has one in the US. Um, and these are places where you could contract these tests to be run. Um, so there are options. There are test houses that do it, but it's a chassis dynamometer, and for the certification, it's usually climate controlled.
Okay. Can you say a little bit more about measuring CAN bus in parallel with the other measurements?
Yeah. So we're going to directly measure the CAN bus into the same data file as the measurements. And the value of that is that you can understand exactly what the vehicle controller is thinking um, while you're measuring, the reality of the signals. So you can look at the calculated values that your inverter is thinking, and then you can look at the real measured values and compare them. But as far as tech specs, I think we can measure right around 1,000 channels of CAN directly in. So you can really look at all those values and here's what my vehicle's thinking, here's what I'm actually measuring. Those are time synchronized as well as CAN can be, and give you a really nice picture as to what's happening.
All right. Well, everyone, we appreciate your time today, and we hope you enjoy the rest of your day. Thanks, Mitch.